Hi, I'm Wolfgang Wein, and I'm happy to present our work on 3D thyroid assessment from untracked 2D ultrasound clips. Medical ultrasound is two-dimensional, difficult, and very local. Therefore, 3D measurements are typically taken on line measurements of 2D planes and then multiplied, for instance, with a magic number for the thyroid. So in many clinical applications, true 3D imaging is desirable. However, either requires a cumbersome setup or expensive hardware such as a matrix array probe shown here. And for externally tracked setups, my very first MICCAI paper 15 years ago actually involved head and neck reconstruction with an external tracker. So what we want to do now is try to develop algorithms for a full 3D reconstruction and volumetric measurements from arbitrary DICOM ultrasound clips without any extra hardware necessary. Now, deep learning based segmentation here of the thyroid gland is now state of the art. We have it as a standard unit and our results are shown on the top right. We've also proposed a method for 3D pose estimation from untracked 2D ultrasound clips 3 years ago. That is also used in products by now. However, there is still some accumulated drift between the frame-to-frame measurements that we're doing here with deep learning. So we're combining this with another idea that we so far mostly used for image-to-sensor calibration, which is that we can reconstruct perpendicular overlapping ultrasound clips for calibration. And we've also done some multi-sweep stitching work with an image-based optimization of overlapping data. So these are the kind of things we want to combine in this. So this is an overview of the method. There's a single transversal clip of the neck and a sagittal clip taken on one lobe, one side of the patient. We run a standard unit thyroid gland segmentation. We run our deep learning based pose estimation of each sweep. We then combine them with the first linear co-registration, followed by a novel trajectory refinement that I'll present in more detail, and a final compounding and segmentation to put it all together. So in the remainder of the method section, I will focus on these 3 steps. The initialization starts with the GPU volume compounding after the deep learning based pose estimation on both the B mode and the segmentation volume data. There are some morphological operations involved, and then we initialize the registration by matching the center of mass and assuming a perpendicular orientation between transversal and sagittal clips. And this is followed by an image-based registration of the B-mode volumes with a standard local cross-correlation approach. This gets us from this separate clips to a first estimated superimposed registration. The trajectory refinement step now that we're adding onto this is here. Here we're going back to image frames, and we actually optimize on 2D frames the similarity of the image with a reconstruction from the other sweep, each with increasing degrees of freedoms onto the rigid pose between the sweeps per sweep. So there's 2 times the number of following parameters that I'll introduce. So we start with 2 more parameters, a single stretching the sweep and shifting it for each of the sweeps to take care of the biggest accumulation of drift. The next step has a full rigid pose for each sweep between first and last frame. Then we add a control point into the middle of each sweep, and then 3 control points. We also developed a probe pressure deformation model with 3 extra parameters that map the top of each ultrasound plane onto a single plane, and then propagating the compression down into the image frame. This is visually working very well, however, numerically difficult to optimize because both of the frames now become moving images. And so we haven't used it in creating the results at this point. For our experiments, we've done volunteer acquisitions with 9 subjects and 180 clips on both sides of the neck in total. We have a ground truth setup with a Cephasonics ultrasound machine and external optical tracking. The volunteers are nicely split into training and testing for the deep learning methods. Segmentation labeling is done on 58 of the sweeps, and pose estimation for the deep learning prediction of the pose is, of course, implicit through the ground truth track. Here's our results. So we actually have a segmentation dice between our deep learning thyroid gland reconstruction and manual segmentation of 85% on the 2D images, which drops to 73% on 3D, which is in sync with existing literature. So therefore, we actually use the deep learning segmentation as surrogate ground truth for the rest of the evaluation, such that we can actually use all of the sweep combinations for the rest of the details. We basically have a 45% error with respect to our external tracking ground truth with our methods from 3 years ago, used alone, and with the trajectory refinement and redundancy exploitation we're down to 14%. This is a scatter plot of the thyroid volume with ground truth tracking versus our estimation. And here we have a comparison with the ellipsoid method, which is much more, so it basically, ellipsoid method underestimates the volume a lot in this case, actually, which is why there's so much debate going on about this magic number that it's being multiplied with. Here a brief illustration of the different trajectory refinement steps. So this is after rigid initialization. You see on the superimposition in the top right how this works. This is after the 2-parameter sweep drift compensation. This is after rigid per sweep. This is after a single control point. This is after 3 control points. This is with the deformation where now all the superficial structures also very nicely match, actually. Interestingly, the ground truth yields very poor anatomical structure alignment, which is expected since nothing image-based is happening in the ultrasound frames. There's an ongoing clinical study with MICCAI in Canada where regular patients are being scanned with a regular clinical protocol. In addition, volumetric scans are taken with this VL13.5 transducer that allows us to do some extra validation, and independent radiologists are taking measurements with the ellipsoid formula. We're then developing a slice to volume registration with a similar reconstruction model as the one that I presented to create sort of an alternative ground truth on actual clinical data. Here's a visual example. We also have a linked visualization where transversal and sagittal are linked when you move around the point and the lines. And our reconstruction volumes vary less than the ones taken by the radiologists. In summary, we try to propose a very general approach for exploiting redundancy in overlapping ultrasound data from different angles, combining deep learning and image-based reconstruction. Presented it on thyroid, but we believe that it's applicable to many other clinical applications. And in the future, we want to extend this to pathology, of course. We can add interactive steps, such as clicking on a single point for reconstructing difficult cases. We want to improve our deformation model to also be more realistic deep inside of the anatomy, detect a forth and back motion of the probe, and improve ground truth, because we've seen that from the external tracking alone, the internal reconstruction is not very accurate, so we're using these volumetric probe measurements, but we could also use high-resolution CT MRI that is a different modality, but has poorer resolution typically than ultrasound. So none of these 3 options are actually suited for perfect ground truth, so there's much more also academic work to be done to get to the bottom of this and yield the ultimate accuracy, basically, for this kind of application. Thank you very much for your attention, and this is it